Welcome everybody to the first Resenha Cosmica podcast. Apologies for any audio issues, as this is the first one. So today we are going to talk about the Euclid telescope, which is being launched Saturday. So Prajwal.
Yeah. Hi. I'm very excited to talk about Euclid today.
Nice. So what is Euclid? What have we got going up into space there?
So Euclid is, as you said, it's a satellite mission. So we are sending this cosmological satellite, which is aimed to do some measurements which are very much needed for the present day cosmology research. It is supposed to do some measurements and, for example, finding out, having a full scale map of the 3D map of the cosmic history, and having a big survey, redshift surveys. It is going to detect 10 billion of astronomical objects. It's going to see almost 10 billion astronomical objects, and it is going to do spectroscopy. And with spectroscopy, we get some good position measurements, and also from it comes the cosmology, the evolution history, the cosmic expansion, and so on. So Euclid is a very exciting mission, which all cosmologists are looking forward.
So you mentioned Euclid is a cosmological telescope, right? And we're going to be probing cosmology. What kind of things do we look at in cosmology? So, what are we trying to find out here?
Yeah, so in general, the cosmology has some probes with which we understand the dynamics of universe and how it is, where it is going. So there are certain probes which cosmologists use. For example, the easiest ones coming from like distance measurements. So, for example, when we look at in the night, during the night, when we look at the cars coming towards us, we measure the distances according to the brightness of the headlights we see. But the point is, the headlights have to be calibrated. We should know how bright the headlight is, because the headlight can be mimicked by a torch, for example. So we need to have certain standard torches in the sky. So there are certain standard torches like supernova type 1A. So these supernova type 1A are very standard candles or standard torch in the sky. So with which we can know we know the luminosity or the brightness of this object. So we can know the cosmological distance to it. This is the same mechanism which Hubble did 100 years ago to measure the expansion of the universe. But when we did it in the late 1900s, we saw that when we measure the distances to the standard candles, we see that the universe is actually expanding, there is an accelerated expansion to it, not just an expansion. So supernovas are key probes in cosmology. So there are other probes, like there is, of course, the cosmic microwave background, which is the first light of the universe, the surface of the last scattering, what we call. And there is, of course, there are very many others like baryonic acoustic oscillations. Then there is large scale structures, which gives us more information about the evolution history of the cosmos.
Okay, cool. And so, like, what do we know about the universe to date from these kind of things?
Yeah, as I pointed out, I would rather say like we are making significant progress with the new observations, with the new discoveries through observations. Because as I said, the accelerated expansion the discovery of this accelerated expansion in the late 1990s was a very key role, played a very key role. So this accelerated expansion of the present day universe is coming from a mysterious exotic fluid which is which is kind of repelling, giving a anti-gravity kind of force, which is pulling things, galaxies apart. They are pushing them much more than a simple expanding universe. So then we also have, when we measured individual galaxies and the rotation curves in the edges of the galaxies, so we also see that there should be more matter to explain the high velocities near the edges of the galaxies, of the stars. So stars are moving more than what they have supposed to be. So this also led us to claim that there should be extra matter, which is the dark matter, which we call. So we don't know what these dark energy or dark matter actually are, but we know that they do exist. For example, dark matter plays a very important role in the formation of structures and so on. So today's cosmology has many open doors, like exploring candidates of dark energy, dark matter, and yeah, it's a very exciting time in cosmology.
So then to bring it back to Euclid, so what role is Euclid going to play in investigating these things?
Yes, so Euclid, I think we'll discuss in more detail with Valerio, who will give us more insight towards it. But the major things which Euclid, what we are expecting from Euclid is it has, uh, it is going to do a very big survey. It is going to see many astronomical objects. With survey, what I mean is a redshift survey. So it is going to do spectroscopic measurements of I think 10 million of these galaxies, 10 million objects, which gives us at least 50 times better measurements than what we can do on the ground. So these redshift measurements are very important in knowing the distribution, a 2D map of the universe, how the structures form. And Euclid also does weak lensing. At least 1 billion weak lensing measurements will be done. And using this and combining with the redshift survey, we can have a 3D map of the whole universe and see the whole cosmic history, how the structures form. And the most interesting part is we can actually distinguish different candidates, for example, for dark energy. We are now debating whether dark energy should be a standard cosmological constant, or is it a dynamical thing which varies with cosmic time. So, or there is a modified gravity to it. So we can actually distinguish between this constant cosmological constant and the modified gravity, and we can know about how dark matter played a role in our cosmic structure formation. So Euclid is going to advance us in all these levels.
Excellent. Yeah, no, that sounds like no, it sounds like a lot of big goals, anyways, for the telescope. Um, and I think you mentioned in there something about structure formation, dark matter being the seed for structure formation. Could you maybe just briefly give us a little insight on what that is?
Yes. So uh, let's start with how the universe, the early universe, led to the structures what we see today. So we know from after Big Bang, during the Big Bang, the things were a homogeneous and isotropic fluid, a plasma, very high energy plasma. But then, as the universe started expanding, this plasma cooled down, and various matter components inside it decoupled from this plasma. The first among these was dark matter. So, because it was heavier than other matter particles. So, when dark matter decoupled from this plasma, it created some potential, because mass creates potential, gravitates, right? That's what Einstein told us. So, this creates this space time potentials into which matter falls and condenses and leads to all kinds of chaotic objects what we see like galaxies. There are many feedback processes. There are very big stars going through explosions, supernovas, and there is feedback mechanisms and so on, which forms all the structures what we see today. So this is the cosmic history. So this uh, there are many interesting probes which we can use to understand the universe. As I said, dark matter is the key here because it led to the structure formation. So there are two things to point out here. Like for example, what is the nature of dark matter? For example, if the dark matter was less massive, then it would have created a fluffy potential well, not so significant, not what we would expect from a very massive. There is a clear distinction between if what happens to these potential wells if they were massive or not massive. So using Euclid, we can clearly know distinguish how the structure formation happened. We can distinguish between different candidates, whether the dark matter was massive and cold, as we say, or it was less massive and hot, in other words. So this is one of the key important things.
Okay, nice. And so I think as well, then I suppose it'd be good to just talk a bit about how did we investigate these kind of things before Euclid, or how are we currently investigating these things?
Yeah, this is a very interesting question actually, because even if Euclid does some these cool measurements, we should have already done something so that we can have a comparison between two kinds of measurements, right? So yes, this is a very good question because previously what we did was we looked at cosmic microwave background and how it traveled throughout the cosmic history. So when the light from the very beginning of the universe traveled through the cosmic evolution, as I said, all the structure formation things, light has some, as we know, cosmic microwave background, first of all, is a black body radiation. It's very hard to find some anisotropy or some disturbances in the background radiation. This is the perfect black body we have seen. The deviations from it are one part in 1,000 or 10,000 or so. So its deviations are very small. So cosmic microwave background itself is a very homogeneous isotropic map. But as it travels throughout this cosmic evolution history, the light goes through these various kinds of potential wells and causes anisotropies. So these anisotropies can tell us a lot about structure formation, about when dark energy became dominant, and little bit about how the nature of dark energy itself and how it led to how it changed the cosmic evolution, structure formation, and so on. So we already have this kind of idea of these things through CMB, but now with Euclid, we can have a comparison parallelly, and this will certainly advance our knowledge what we have already. I think we were talking about Euclid doing lensing as well. Maybe you can tell us about what actually lensing is.
So we've been talking a lot about dark matter in different ways that we know that it's there, and lensing is one of these ways, right? So the kind of lensing we're talking about is not the usual lensing through a glass or a magnifying glass or something like that we would be used to, but rather it's gravitational lensing. And what we have with gravitational lensing is that a very massive object, which, as you mentioned previously, because of Newton and Einstein and people like this, we know that massive objects have a gravitational field around them. which draws things in. So light is because light is massless, it does behave slightly differently to how a massive object would be drawn in. So where a massive object, will say like the moon, may enter an orbit if it's traveling slow enough to enter an orbit, light travels incredibly fast. So unless it's near an incredibly massive object like a black hole, the light is going to just be bent, right? It's not going to be pulled in or anything like that. The path of it is just going to be slightly curved as it comes past. And what we have then is that if you have a galaxy that's positioned behind another galaxy along our own line of sight, well, then we end up being able to see that galaxy because its light is bent. So this may be slightly contradictory to intuition, in the sense that if you have a wall in front of an object, you're not going to expect to be able to see that object around the wall. But what we have in this case is our wall is an incredibly massive galaxy. And because of this, the light can actually get bent around the wall. And we see an image of that galaxy on the far side of the wall, and it will be distorted. So what happens is that you get this distortion of the image that will appear, if it's directly behind the galaxy, it will appear like a ring around the galaxy which is doing the lensing. Or if it's not so perfectly aligned, it may be just some section of the ring, or you will get some distortion that appears as if it's in a different place than it actually is. So yeah, this is what gravitational lensing is in a nutshell.
Yeah, so this I think Euclid does beautifully, because it combines this with the redshift survey, which it does, and with this it would be very interesting, because then we'll get a 3D map of the evolution. So said this, what are the other surveys we already have today? Like I think there should be some other ground-based telescopes already before Euclid. So can you tell us little bit about what are the other important surveys we have?
Yeah, right. So yeah, in terms of ground-based surveys, we have the SDSS, which is the Sloan Digital Sky Survey. So this is a real pioneering survey in observational cosmology, right? So it provides extensive imaging and spectroscopic data for millions of galaxies out there, right? And what it is it's two separate surveys, right? So we have that the galaxies are first of all identified in 2D images, and then have their distance determined by looking at their spectrum, so that we can look back 2 billion years into the past, so 2 billion light years away, and see what these galaxies looked like then. So yeah, the Sloan Digital Sky Survey looks at, yeah, as I said, millions of galaxies. It maps about a quarter of the sky. So a little less than what Euclid is planning on looking at. So I think you mentioned earlier Euclid is looking at a third of the sky. And yeah, so this is the Sloan. Then we have some other space-based observational telescopes, such as the Wilkinson Microwave Anisotropy Probe, or WMAP for short, much easier to say. And this is specifically for studying the CMB, the cosmic microwave background, which, as we mentioned earlier, again is a fantastic way of learning about dark energy and about structure formation in the early universe. Then finally, we also have we have another telescope. So after the WMAP, we had the Planck satellite, which again is looking at the temperature of the CMB, and as well the polarization of the photons that are coming from the CMB, right? Which again can tell us something about dark energy and dark matter.
Yeah, and also I think Euclid, along with the future surveys, like I think DAISY, which is another ambitious survey which is currently going on, started out. I think it was supposed to be in 2017, but due to the pandemic, I think it was postponed to last year. I think it started last year, and of course, in the next decade, we'll have another big survey, which is LSST, and yeah, so this decade and the coming one is going to be very, very, very big for observational cosmologists and people who do data related works in cosmology. So it's going to be really amazing to see the new discoveries coming up.
Yeah, it all sounds very exciting. So yeah, I think we'll be having our discussion with Valerio on Saturday. Again, it'll likely be before this is uploaded, but yeah, hopefully we see plenty of people on Saturday.